right, angular speed and linear speed. Angular speed was what again? What's angular speed?
Angle over time.
It's the angle per unit of time. So that's another way to write that is how much is one revolution? What's the angle of one revolution? In radians, please. 2 pi. So this is 2 pi would be one revolution times the total number of revolutions per unit of time. So that's the angular speed. That's 2 pi, which is one revolution, times the number of revolutions per time. What was the linear speed again? Well, the circumference, it's not quite the circumference over time, because the circumference would only be good for one revolution. So linear speed.
Oh wait, I was looking at loop here. The circumference. It is the circumference of
It would be the total distance traveled per unit of time. The total distance would be the circumference would be the distance for one revolution, but we might be doing more than one revolution. So linear speed is 2 pi r, which is the circumference, times the total number of revolutions per time. Did I say that? Then I said wrong. If I said that, I was wrong if I said that. It should be the circumference, which is the distance for one revolution, times the total number of revolutions per unit of time. So notice that angular speed and linear speed are almost the same. What's the only difference between angular speed and linear speed? To get linear speed, I take my angular speed and I multiply by r. So linear speed equals angular speed times r. Multiplied by the radius is the only difference between the two. Angular speed is, if you have something spinning, let's say you have a wheel.
Is it how fast it takes?
It is related to revolution. A wheel does 6 revolutions per minute. What is the angular speed? Well, our answer would be angular speed is how much of an angle is one complete revolution? 2 pi. And this is doing 6 revolutions per minute. So our answer would be 12 pi radians per minute. So that wheel, the angle that's happening, every minute that wheel is going through an angle of 12 pi radians.
So, angular speed is
Correct. Times 2 pi, because that's one complete revolution. Yep. Linear speed is like right. Linear speed is like the speed we're used to dealing with, like 20 miles an hour. That's the linear speed. How far are you going per unit of time?
So if you had a circle, you would measure. I guess you would measure, but the linear speed you would line from the center of the circle, and the circle goes over here, and then the angular you measure it by how much it goes like that.
Yes, that's a good way to think about it. Now can I draw that? So what Ian just said is if I have a circle, and the circle goes from here to there, the linear speed would be this distance, starting from this center to that center. The linear speed would be that distance divided by however long it took. That would be the linear speed, which is our normal 50 miles an hour or 20 miles an hour or however fast you walk, run, drive your car, whatever. The angular speed, on the other hand, would be how fast is this thing spinning around and around and around as it goes? So what angle, and when will it stop? So the angular speed would be the total angle that the thing went through divided by the time. So you'd have to figure out how many revolutions it took to go that far, and you would add all the angles together, 2 pi every time it did one complete revolution to get to there. Okay? The evolution of a what? A guppy? I didn't know that. All right, so go ahead.
If you were able to draw the path of the angular speed, would it turn out to look like a cosine or sine curve?
Well, the angular speed is just a constant.
Okay.
What you're thinking of is if I pick this point right here
Yeah.
and I let the wheel roll,
Yeah.
then yes, absolutely, this point would generate a wave that looks like that. Absolutely.
Okay.
Because it would start high, it would roll, it would eventually be down at the bottom,
Yes.
and then it would roll back up. Absolutely. In fact, that's how we defined sine and cosine, was by taking a circle
Yeah.
and mapping the x values and the y values as we went around. So yes, absolutely. All right, so this was a problem that we had from the worksheet that I passed out last time. It says we have a truck with 48-inch diameter wheels, and this truck is traveling at 50 miles an hour. Determine the angular speed of the wheel in radians per minute and how many revolutions per minute the wheel makes. All right, so we have a truck with 48-inch diameter wheels. What does that tell me? Radius is 24 inches. Okay, and then it says this truck is traveling at 50 miles per hour. What's 50 miles per hour? That's the linear speed. Our typical speed, 50 miles an hour. That's our linear speed. So linear speed is 50 miles per hour. Determine the angular speed. So we need to know the angular speed. And we need to know the number of revolutions per minute. All right, and how are you coming up with that? I said linear speed is angular speed times r, and you're absolutely correct. That's what I said. So the answer is the linear speed, 50 miles per hour, equals the angular speed times the radius, which is 24 inches. So the angular speed is 50 miles per hour divided by 24 inches. I cannot, however, just grab my calculator and go 50 divided by 24. Well, I can, but I won't get the right answer. Why not?
Because you have
They're different units. 50 miles per hour, 24 inches. Can I divide miles by inches? No, I need to fix my units. So that's the right answer, but to get the answer we really want, we got to fix our units. So we have to make a decision. Do we want to convert 50 miles per hour into inches per hour, or do we want to convert 24 inches into miles? How many inches are in a mile? I don't know. A lot.
It's like 5,000 feet.
All right, so I think I would go with 24 inches. 24 inches is 2 feet. And how many feet are in a mile? 5,000 something? We should Google it. So now all of us live in the United States of America where we use the feet, inches, miles. Shouldn't we know the conversions? I guess.
I've been asked how many feet are in a mile.
This is why we use metric, because it's easier. If it were metric, we just multiply and divide by tens. It would be very simple. I know. Well, that's not. I didn't pick it. All right. So there, 1 mile is 5,280 feet. You knew?
No, I did.
Oh, you knew. All right. Very good. 1 mile is 5,280 feet. If you needed that information on a test, I would give it to you. I would not force you to memorize that there are 5,280 feet in a mile, but you should. You should know that. Like I say, we all live in this country. All right, so we reduce. What's 2 divided by 5,280? Why did I write what like who? Because to convert units, I think of everything that's fractions. So if I have 2 feet and I want to convert it to miles, I need miles on top and feet on bottom so that my feet reduces with my feet and I'm left with miles. Yeah, then you do that kind of conversion stuff a lot in chemistry, don't you? I got 1 over 2,640. Is that correct? Yes? All right. So our correct answer should be 50 divided by 1 over 2,640 for our angular speed. What's 50 divided by 1 over 2,640?
50 times 2,000.
132,000. And our units would be, angular speed is in radians per time unit, so that would be radians per hour. So this wheel spins round and round and round. 132,000 radians in 1 hour. Because our original units were miles per hour.
Oh.
So our time units in this problem is hours all the way through. Wasn't that bad? All right. Now we want to find how many revolutions per minute. What did I say about angular speed? Angular speed is 2 pi times revolutions per time. Oh, crap. No, I did not mess up. I didn't give the right answer because it says determine the angular speed in radians per minute. I gave radians per hour. Do I multiply by 60 or divide by 60?
Just cross out.
No, you would multiply by 60.
So it's 792,000.
You would have to, because you have 60 minutes and 70 minutes. No, dude, that's hours.
So if I want to get rid of hours and convert it to minutes, I need to multiply by 1 hour so that I have hours on top and hours on bottom and they cancel out, which means I need to have 60 minutes down on bottom, so I should divide by 60, not multiply by 60. That's why you do that unit thing like you do in chemistry. So it's 132,000 divided by 60. 2,200. How much? 2,200. That's enough zeros?
That's
I'm going with 2,200 radians per minute. All right, so there's my angular speed. And then it asks, how many revolutions per minute? Well, my angular speed is 2 pi times revolutions per minute. So if I know the angular speed, how do I find the revolutions per minute?
2 pi times 2,000.
No, other way. I know this number. I know my angular speed.
Oh.
I'm trying to find this number. So I'm going to need to...
2,200 equals 2 times x over 1.
So I'll divide both sides by 2 pi. So my, ran out of room here. I don't know where to write it. I'll write it here, I guess. The revolutions per minute is 2,200 divided by 2 pi, which is 1,100 divided by pi.
Why is it divided by?
Because angular speed, this is a number we just figured out, that's 2,200, equals 2 pi times our revolutions per minute. So to get revolutions per minute alone, I divide both sides by 2 pi. So about 350 revolutions every minute. So that tire is going around and around and around 350 times a minute, roughly. Pretty fast. All right, so the interesting thing with that, well, maybe not interesting, the hard part of this problem is not really using these formulas. The hard part is the fact that it gave you stuff in miles per hour, then it gave you inches here, and then it asked for answer in radians per minute. The hard part is keeping track of all the units and converting things around. That's the part that really stinks on that problem. But that's pretty typical of these problems, so we'll have to deal with it. All right, so let's try number 8. Number 8 says, the sprockets and chain of a bicycle are shown in the picture. The pedal sprocket has a radius of 4 inches. So that's this one, 4 inches. The wheel sprocket has a radius of 2 inches. So that's this one down here. And the wheel has a radius of 13 inches. So that's this one. The cyclist pedals at 40 revolutions per minute. Determine the angular speed of the wheel sprocket. So again, that's this little one here. And determine the speed of the bike. All right, so we have that the big sprocket, this is this one. The cyclist pedals at 40 revolutions per minute. So that means the big sprocket is going 40 revolutions per minute. What? Where'd what come from? This one, that's right. The big sprocket. That's the big one, this is the little one. See? That one's smaller. All right, if the big sprocket is going 40 revolutions per minute, how fast is the little sprocket going? Why 80? Because it's half the size, which means it has to be going twice as fast. So the wheel sprocket, if you prefer, I can't spell wheel. Wheel sprocket, which is the little sprocket, is going 80 revolutions per minute. If the little sprocket, if the wheel sprocket is going 80 revolutions per minute, then how do I find its angular speed? Well, we look back at our formula here.
2 pi. Wait,
Angular speed is 2 pi times revolutions per minute. So our angular speed is 2 pi times 80, which is 160 pi radians per minute. So that's the angular speed of the little sprocket. I think writing down units for these problems is extremely important, because if you don't write down units, there's absolutely no way you're going to get problem 7 right. So yes, I think on these problems like this, it's extremely important that you write units down. All right, so the angular speed of the little sprocket is 160 pi radians per minute. What's the angular speed of the tire? No. All right, so this little sprocket right here is spinning at 160 radians, 160 pi radians per minute. If this one's going 160 pi radians per minute, how about the wheel? What's its angular speed?
They're usually going the same because they're attached to it.
The angular speed of the wheel and the angular speed of the little sprocket are exactly the same, because they're attached to each other. The angular speeds are the same. It's the same circle, basically. You have concentric circles, but if this one goes 1 revolution, this one goes 1 revolution, because they're physically connected. So the angular speed of the little one is exactly the same as the angular speed of the big one.
No, it's not asking about angular. What's linear?
Ah, so the final question is determine the speed of the bike, which is the linear speed. But the important thing is that linear speed is angular speed times radius. So I needed to know the angular speed of the big wheel. So how do I find its linear speed? I multiply by the radius. So linear speed is going to be 160 pi times the radius is 13 inches. So it's 160 times 13.
Divided by 13?
No, times. Because 2080 pi. Because linear speed equals angular speed times radius. So I just took my angular speed multiplied by 15. And this would be in what units? At the speed, linear speed, inches per minute. Linear speed is our normal speed, like miles per hour, except in this case we're not using miles an hour, we're using inches a minute. So our linear speed, the speed of this bike, is 2080 pi inches per minute. Is that very fast, or is it kind of slow? It's really slow?
No, isn't that good? Because
Isn't it good?
Inches per minute?
Because what is it? 5,000 inches.
No.
What?
Oh, that's the speed. That was the speed.
Divide that by 12. That's 173 feet.
All right. So let's see. 2,080 pi inches per minute. All right. So let's deal with the minutes first. There are 60 minutes in 1 hour. So the minutes reduce. Don't reduce to 60, though. You got to multiply by the 60. And then, how do I turn inches into miles? Now that's to turn minutes into hours. I times by 60. How do I turn those inches into miles?
Well, I multiplied that by 12.
So
Wait, 2008.
12 inches is 1 foot. So I divide by 12 to change to feet. And then I would have to divide by 5,280 feet in 1 mile. All right, so you're going to take 2080 pi, you're going to multiply by 60, and then you're going to divide by 12 times 5,280. So grab your calculator, tell me what you get.
You get just under 2 miles an hour.
Just under 2 miles an hour?
Well, see the way I did it, but I did it 2000. divide by 12. And I got that, and I'm going to go that by 60. Because that was per minute. And so in an hour, you actually go 10,400. So I guess I could divide that by 5,000.
Because he forgot to multiply by the pi. And all the words he said, I never heard the word pi. So this is about 6 miles an hour. You forgot the pi, Graham. I heard all the other numbers. I never heard you say I multiplied by pi. So 40 revolutions a minute on this bike. That's about 6 miles an hour. Was that very fast or very slow? For a bike, that's pretty slow.
It's like a leisure.
It's a pretty slow bike ride, yeah. I mean, people can pretty easily run 6 miles an hour. Not me, but people can. Bike ride, I would say, 12 to 15 miles an hour is more decent speed for a bike ride.